last video from chapter 18, we're going to consider the Michael addition. Which is the addition of the enolate to an alpha unsaturated carbonyl compound. And the related Robinson annulation which forms new rings, often 6-membered rings. And annulation refers to ring formation. And the Robinson annulation is a Michael addition followed by an aldol condensation. Intramolecular aldol condensation. So it's a way of taking cyclohexanone, for example, and making bicyclic structure like that. First step is to make an enolate. Then we can add another carbonyl compound, like, for example, methyl ketone, which we saw in the previous video. And in fact, anytime you see methyl ketone as a reactant, immediately be suspicious that the reaction that's involved is the Robinson annulation. And then in the third step, work up. But as long as there's still base present, when we have the methyl ketone, we will do a conjugate addition, but then we won't stop at the conjugate addition. We'll actually end up doing the Robinson annulation as well. So let's look at the mechanism for this reaction. Synthetically, this is a big challenge because when you're thinking about doing this reaction, it's very tempting to try to make this carbon that carbon. But this carbon is not that carbon. This carbon is this carbon. Carbonyl carbon in my product actually comes from the methyl ketone. So if I were to number the carbons in my starting material and in my product, which is often a good way to try to figure out what's happening, if I number this carbon 1, 2, 3, 4, and then number around this ring 5, 6, 7, 8, 9, 10. Carbon 1 is here. 2, 3, 4, 5, 6, 7, 8, 9, 10. So my new carbon-carbon bonds are in fact this one between carbon 4 and carbon 6, and this one the double bond. We know that the product of an aldol condensation is an alpha beta unsaturated carbonyl compound. And when we work backwards from an aldol condensation, we're always adding water across the double bond, putting 2 hydrogens on the alpha carbon and an oxygen on the beta carbon. So when we see this alpha beta unsaturated carbonyl product, we know that this bond is formed by aldol condensation. And this UCC sigma bond is formed by conjugation. And the conjugate addition of the enolate ion to an alpha beta unsaturated carbonyl has a special name of microaddition. So now that we've figured out what's going on, we need to form a bond between carbon 4 and carbon 6, an alpha carbon of cyclohexanone and the beta carbon of the methyl vinyl ketone. And then we need to form a bond between carbon 1, which is an alpha to the carbonyl of the methyl vinyl ketone, and carbon 5, which is the carbonyl carbon of my cyclohexanone. The full mechanism of the Robinson annulation will be 8 steps. The Michael addition will be 3 steps, and then the aldol condensation will be the usual 5 steps. See Michael addition. That's a conjugate or 1,4 addition. So if you know ahead of time that you're doing a Michael addition followed by an aldol condensation, logically you can determine if there are going to be 8 steps. First step is to use my base to remove the alpha hydrogen before we accumulate all that. Second step is the attack of that enolate ion on the beta position of the alpha beta unsaturated carbonyl compound, doing that 1,4 conjugate addition. And there's nothing special about the Michael addition. It's just a conjugate addition, but it's conjugate addition where the nucleophile is the enolate ion. And the electrophile is the alpha beta unsaturated system. So we'll regenerate the ketone in the 6-membered ring, form our new carbon-carbon bond. Oxygen where it's both stable. Third step is proton transfer. Protonate that enolate ion. In this case, since I'm doing this in ethanol with sodium ethoxide as my base, proton source. You'll notice that the product of the Michael addition is a 1,5-diketone, or a 1,5-dione. I can write that more neatly by straightening out my chain. And you'll notice that I have my two ketones. Additions 1 and 5 relative to each other. I made a new bond there between carbon 3 and carbon 4 in that 1,5-dione, right, which was the beta position of the methyl ketone. The reason I drew it like this is to put carbon 1 from my original numbering scheme close to carbon 5 from my original numbering scheme, because I knew I wanted to make a bond between those two for the 600 ring. So now what I'm going to do is an intramolecular aldol condensation, where I take the hydrogen off the methyl group, get an enolate ion, step 1 of the aldol condensation is step 4, equal for all reaction. And you'll notice that the net effect of steps 3 and 4 are to move a hydrogen from the methyl group over to the other position. I'm simply switching enolates. I have an enolate on the more substituted side. Now I'm forming an enolate on the less substituted side by going through the diketone entity. This can come around and attack the carbonyl compound, forms a 6-membered ring. This is stable. So step 5, I have our filler attack. Enolate on the carbonyl. Generate alkoxide. Now we're going to propionate that to step 6. And again, we're going to regenerate our base, our ethoxide ion. And since it's an aldol condensation, product of this reaction beta-hydroxycarbonyl compounds are the products of the initial aldol condensation. 3 steps, steps 4, 5, and 6 of my overall pathway. Now I have my base. I have another alpha hydrogen. So again, moving alpha H to my enolate. Process. Reform that carbonyl, form carbon-carbon pi bond, and push off that carbon as a amino group. Creating the carbon-carbon double bond between the original carbonyl carbon. Started out like right over here. And then follow the reaction. Becoming alcohol after step 6. And the beta position of product alpha beta unsaturated carbonyl. So one alpha beta unsaturated carbonyl compound, ketone, becomes a second alpha beta unsaturated carbonyl compound in the formation of another ring in Robinson annulation. This is step 8. Step 5 of the aldol condensation. So on the top of the board, we have the 3-step Michael addition, enolate formation, conjugate addition, and proton transfer to make a 1,5-dione. And on the bottom of the board, we have the 5-step aldol condensation, enolate ion formation, nucleophilic attack, enolate on the second carbonyl, protonation of the alkoxide ion, removal of the additional alpha hydrogen for a new enolate ion, and then elimination of the hydroxide leaving group to form the alpha beta unsaturated carbonyl compound. Potentially isolable at the 1,5-dione, potentially isolable at the beta hydroxy ketone stage, but the driving force for the reaction is formation of that big stable alpha beta unsaturated carbonyl compound at the bottom right of the board. So 8 steps, not the longest mechanism you've seen, but not the shortest either, to do the Robinson annulation. Very synthetically useful, especially if what you're after is polycyclic compounds or 2-ring system. This intramolecular aldol condensation we showed down at the bottom here is effectively a cross-aldol condensation. Just a cross-aldol condensation that's happening from the 1,5-diketone. So the question you might have is, why do we just get one product when we have 2 carbonyl compounds, and both of those carbonyl compounds have alpha hydrogens, and can therefore potentially act as either donors or acceptors? Why don't we get a complicated mixture in the case of Robinson annulation? Why do we get just one product? Because if you look at that 1,5-diketone, there are 4 different types of alpha hydrogen, which means that in theory, when treated with base, 4 different enolates can form. So the question is, why don't they form? And the answer is no reason. They do. All 4 possible enolates can form. So we can get a mixture of 2 different enolates from 2 different alpha hydrogens. In the 6-member ring, and 2 different enolates. This bottom one was the one that led to the product through addition to form beta hydroxycarbonyl compound that looks like that, followed by nice stable 6-membered ring. That's the product we isolate. So the question is, why can't these other enolates, once they're formed, and they're going to form, the acidity difference between the hydrogens is negligible. The most stable of the enolate ions is in fact this one, which has the double bond with no hydrogens on it, so it's benefiting the most with hyperconjugation. So why doesn't this one do that intramolecular aldol condensation to form a beta hydroxyketone? Well, the problem is that was over 4-member ring. So it could theoretically form, but the 4-member group is not very stable. And furthermore, there's no additional alpha hydrogen, which means it would be stuck at this beta hydroxy ketone and unable to go on to the alpha beta unsaturated compound. So does this beta hydroxy ketone form? Quite probably. But since all of these steps are equilibria, including the enolate ion formation that happens initially, it's not going to stay here. It's simply going to revert back to the diketone and then be deprotonated in a different position. This could also come in, attack the carbonyl compound. And again, you're going to see that this is a 4-member ring that's forming between this carbon 4 and this carbon 1. So it's going to form right. Put my hydrogen here. carbon-carbon pi bond like that in a four-membered ring has a great deal of ring strength. Even more than this sp3 hybridized ring. When you put sp2 hybridized carbons in the ring like that, and try to make them 120 degree bond angles, that's a long way from the 90 degree, further even than the 109.5. So could it happen? Yes, it could, but it's not going to be stable. It's not going to stay there, and it will simply revert. That leads to the question, what about this one? That's going to form a 6-member ring. And there will be additional alpha hydrogen. So why doesn't this one? It'd be a little bit difficult to draw this one. Because it's actually going to form a bicyclic structure. Steps could potentially form that. There's really no reason why that can't form. It's a beta hydroxyketone. We have this additional proton. It could theoretically be moved. The problem is you're now putting an sp2 hydrocarbon out of the chip. And if you come in, try to take that hydroxide out, you're still putting an sp2 hybridized carbon out of the chip. Now a carbon-carbon pi bond. You can't do that because of the geometry of that molecule. It would be too much ring strength to get. If we redraw that molecule, carbonyl group is that bridge. It's a 6-member ring. Another 6-member ring. And what we're trying to do is put a carbon-carbon pi bond in this bridge position. That's not stable. Because if you think of this as kind of a twisted boat, this overall ring now is an 8-member ring, and we've got positions 1 and 5 kind of bridging. Turn this. So we've got here, there needs to be something kind of sticking out. There needs to be a hydrogen here because these three are kind of held into a pyramid. Bond angles can't be 120. Normally, the way that molecule would be drawn, this would be an equal sort of position. Carbonyl, axial position relative to the 8-member ring. That's just not going to be stable. So because of this instability, the inability to put a pi bond at bridge end, the inability to put a carbon-carbon pi bond into a 4-member ring, there is a ring strain, and the lack of an alpha hydrogen and 4-member ring problem in the other compound, the only one where we end up with no ring strain, with a nice carbon-carbon bond, and in the cyclohexane, right, 120 bond angle would create equal for regular hexagon. The only stable product is this one. So while all 4 products could potentially form, right, of intramolecular aldol condensation, only one of those intramolecular aldol condensation actually leads to a product that's stable enough to stay there, and equilibrium will eventually drive towards the only significantly stable product. And that finishes chapter 18. It's our survey of reactions of aldehydes and ketones, and we will move next into